Good morning, friends. We have been discussing about the issues or the type of alertness we need to have when you use brigade relationship to compute range, endurance for a jet airplane, for propeller-driven airplane. We have also talked about lift to drag ratio. These all have been done to get an initial feel for numbers. We'll have one session where we'll be talking about how to use historical data to get an estimate of, initial estimate of L by D for the airplane which you are going to design. Please understand that so far, last few lectures, we are preparing ourselves to calculate or to estimate the initial amount of fuel required for a particular mission requirement. So I thought today I will take one example from a book, Raymer, aircraft design book by Raymer, which I've been following now for some time. And there is one example given in that book, and I am trying to share that example so that if you have that book, which you must have, if you are really interested in design, and you can read the book, and these two things will complement each other. But do not forget one thing. Whatever we give in the book and whatever I am telling, they have been validated through limited experimental data, limited statistical data. At the same time, the technologies are changing very fast. So how good will be those data, whatever available last 10 years or 10 years ago, is a big question. So best way to handle this is understand fundamentally what you are doing and try to put your insight into it. And that is the whole purpose of this level 1 aircraft design course. So we'll now quickly take the example. I repeat, this is an example given in Raymer's book. What is the mission requirement given there? That crew weight is 800 pounds. Remember, we want to measure or estimate, we want to estimate what is the initial gross weight, and we say that is equal to W crew plus W payload plus W empty plus W fuel. Right? We segregated it like this, right? And then we have shown I can express W not equal to W crew plus W payload by 1 minus WF by W naught minus WE by W naught. We have also discussed how to get WE, that is the empty weight fraction, using the historical data. But last few lectures we are working towards a procedure so that I can find WF by W naught, that is how much fuel is required, to get an idea of that. So now we have done everything required for that to get an estimate, initial estimate of WF by W naught. We'll try to see how far you have understood what is the method through an example. The example is crew weight is 800 pound, payload avionics maybe 10,000 pound. We want to fly at Mach 0.6 at an altitude 30,000 feet. You will find where you are using a jet-driven engine, the optimal altitude is around 30,000 feet tropopause. All those details will come as we grow. Just to see how to compute fuel consumption, we are taking some number. And remember, when I am talking about Mach number, I need to know what is the speed of sound at 30,000 feet. And that is 994.8 feet per second. And the aim was, you take off from one point, go to a range of 9,114,000 feet, maybe around 1,500 nautical miles. So I go take off, climb, go to that 9,114,000 feet, but then I have to again come back. If that is my mission requirement, which is like a transport airplane, I'm designing, or a fighter airplane I'm designing, or a combat airplane I'm designing. One could be I take off, go do the operation, and again come back to the base. So if that is the situation, then I have to add this range as an additional range, right? So the airplane has gone from here, climb, did its operation. Now again it is coming back here. So I am adding this range twice. 91400, and I am adding again 91400. That is the understanding. It is not necessary that I have to do it every time. I may just come from here and land here. Possible, right? Some distance, not on the same point. But this example is telling I'm taking off, climbing, going for a range, and I'm again coming back to the base. That means I have to cover that much range as well. That is why, although R is designed for this feat, this example, I'm taking additional range this, assuming that operation is happening like that. And it depends upon the user how to define range from the mission requirement point of view. It's just a number. More important thing, how do I get what are the fuel consumption, or what is the fuel consumption. Okay. So now we have 0 to 1. This is we call warm up and takeoff segment. And if you see the historical data, you have to look here. You have to look here. Historical values that are based on historical data, different type of airplane. But please understand, when I am designing a mission requirement of this class, I must select a baseline airplane. Okay, that is, some airplane will be available which will have capabilities closer to this. So I pick that airplane. Okay, to get the initial values. The historical value, it has been recorded that generally W takeoff, that is for 0 to 1, W1 by W0, this is typically 0.970. This is a fraction, right? And every initial design stage, we are taking this value. Then similarly, from 1 to 2, which is climb, this is W2 by W1, again based on historical value, it is 0.985. These are initial estimates. So once you freeze the airplane and start evaluating in a refiner manner, these numbers will get modified. But these are good enough initial estimates based on historical data. So I know W1 by W0 is this, W2 by W1 is this. So let me write it here. W1 by W0 is 0.970. W2 by W1 is 0.985. Okay, and let me erase this. So I have handled 0 to 1, warm up and take off, then climb. This is 2. Now I'm going for first range, which is around 9114 000 feet. So up to this, if I put a 0.3 and 0.4 here, this is representing a loiter. Let's say the loiter in that example is for 3 hours. Then it goes again, comes back, again loiter for 30 minutes and land. This is the mission requirement. Okay. So if I modify this diagram, I write here loiter 3 hours and loiter here also for half an hour or 30 minutes. Then land. This is clear? So what I am doing, I am warming up, take off, climb, cruise, loiter, again cruise, this comes like this. Or I can interpret it like this, warm up, take off, climb, go to the range, loiter for 3 hours, again I come back. This is the same. That is why I have added the range ones. You see, 91400 and then again 91400, because that is type of mission I am doing. Okay. Now what is W3 by W2? Why we are interested in W3 by W2 or W2 by W1 or W1 by W0? I am trying to see what is the weight W1 after it has done the operation from 0 to 1. So that will give me the fuel consumption, because W0 minus W1 will be the fuel consumed at that point. So W3 by W2 will be what is the fuel consumed during this operation. Once I know W2. So we know this is 2 to 3 is cruise. So I can write R equal to 9,114,00 feet. This is a requirement. And C, we have seen typical jet SFC cruise. We have decided to take turbofan high bypass ratio. Why not low bypass ratio? Why high bypass ratio will be discussed later. Just now we are assuming that these things we know, then how to calculate the fuel fraction. So I again come to the turbojet or typical SFC for jet. I could see pure turbojet, then for cruise I should take the value of C or SFC as 0.9. If it is loitering, then it is 0.8. But we are interested in high bypass ratio turbofan. So I will take 0.5 for the cruise and 0.4 for the loiter. These are again based on historical data. So I take 0.5, and if you see in the table, it is given per hour. So this is per hour. So we need to be very careful when you use such tables. See the unit, but you have to convert it into per second because we are working in FPS system. So if I do that, this becomes 0.0001389 per second. 0 point. Okay. Now the question comes, what L by D I should take? As I told you, for jet engine, if you are going to maximize range, it should fly at 0.866 of L by D max. And yesterday I gave you an example. We'll also have one session on L by D max for different airplane. You have seen that the value of L by D max is somewhere between 16 to 20. Dreamliner and all A380 is approaching 20, but it is from 16, 15, 16, 17, 18, around that it will lie generally for this type of airplane. So for the test case, we'll take L by D max as 16. We'll also demonstrate how to take this L by D max using historical data, maybe tomorrow or next class. But 16 is not a bad number, and yesterday we have seen that. Okay. So in that case, then L by D, which will be used for the range, will be around 13.9. This is important, 0.866 L by D. And from the range formula, you will see W3 by W2 can be written as e to the power minus RC by V L by D. Check back the range formula. From there you can find out this. And if I put this value, this will come around 0.852. R you know, C you know, V you know. If I want to compute this, I need to know the value of R, which is given there. C we have corrected for dimension here. L by D, it is around 13.9. What is V? V is 0.6 max mean 0.6 into velocity of sound at 30,000 feet. So the V will be equal to 0.6 into velocity of sound, and that is 94.8. So this becomes roughly 569.9 feet per second. I repeat, to get this ratio W3 by W2, I need to know the value of R, C, V, L by D. All are given. If you plug in, you will get this ratio W3 by W2 equal to 0.852. right? We are trying to calculate W3 by W2. We need to know the value of R, C, V and L by D. R we know, C we know, L by D we know. V, the airplane is flying at Mach 0.6. So V will be 0.6 into velocity of sound at 30,000 feet. And at 30,000 feet, the speed of sound is 994.8 feet per second. If I do this, this becomes around roughly 596, right? Feet, okay, feet per second. This is a rough number. You are supposed to do it yourself. And then W3 by W2 will be 0.852. Okay. Once we have found out W3 by W2, now we are interested in W4 by W3. And what is the mission during W4 by W3? It is about to loiter for 3 hours. Okay. So now loiter for 3 hours. 3 hours means again we have to convert into FPS unit. So this is 10800 second. And what value of C should I take? Since we are using high bypass turbofan, you have seen for loiter, the historical value is 0.4, right? So we take C equal to 0.4. Of course, this is per hour. So to convert into per second, and that will be 0.000111 per second. I repeat again, everybody, to compute yourself and discuss in the forum. And this is for loiter. Repeat for best range, the value of C, SFC for a turbofan with high bypass ratio was 0.5, recommended 0.5, but historically best number is a 0.5. Now, if you go back to the formula for endurance for jet, you will see it is proportional to L by D. So if you want E max, you have to fly at L by D max. Unlike the range case, where you have to fly at 86.66% of the L by D max. So now the L by D max, since we have chosen around 16, so the L by D required for loiter estimation will be also taken 16. And then W4 by W3, if you see that expression and take the inverse, you will get this equal to e to the power minus EC by L by D. And you put the value of E in seconds, 10800 second, C 0.000111 per second, L by D as 16. This value will come out to be 0.9277. Okay, just to give you this value, this whole in the bracket should come minus 0.075. So W4 by W3 is known. Now we want W5 by W4. W5 by W4 is what? What is the operation from 4 to 5? It is again, as per our requirement, we said, okay, let it fly for this much of range. Assuming that it is again coming back to the base. This range could be different. The airplane may land at other distance, some other range, but we have taken, for example, it's coming back, so we are putting 91400 feet. So W5 by W3 will be same as W3 by W2, right? And W3 by W2 was 0.852, so I put 0.852. If this range was different than this, then the ratio will change, right? But since they are same, so I am not doing a repeat calculation. So this value is here. Now comes, this is W5 by W4, no? Sorry, this will be W5 by W4. So W5 by W4 is 0.852, which is the same ratio as W3 by W2 because the ranges are same. Now we want to look for W6 by W5. W6 by W5 is what? We are looking for W6 by W5, that corresponds to loiter of 30 minutes as per the mission requirement, and 30 minutes means 1200 seconds. Again we have to use W6 by W5 equal to e to the power, this is endurance equation, EC by L by D. C we know, E we know, around 1200 seconds, L by D we know, it will be L by D max. So this ratio will come out to be 0.9917. Then comes W7 by W6, which is as per historical data, it is advisable to take around 0.995. As you will start learning more about design, these numbers you'll be refining, right? These are the starting numbers. So what we have done, we have seen W0 by W1 by W0, W2 by W1, W3 by W2, then we have W4 by W3, then we have W5 by W4, then we have W6 by W5, and we have also W7 by W6. So let me write you will not be able to see here. So W7 by W6. Okay. So what to do with all this number? By doing all these things mechanically, with a clear-cut understanding that what units we are using, and many a times we are using historical based data, and this exercise is to get just initial numbers, design numbers for beginning a design, starting a design. We have got W1 by W0, W2 by W1, W3 by W2, W4 by W3, W5 by W4, W6 by W5, W6 by W7. Our aim is to see what is the fuel fraction. Now I multiply this. W1 by W0 into W2 by W1 into W3 by W2 into W4 by W3 into W5 by W4 into W6 by W5 into W. If I write it like this, if I take product of all these fractions, what finally I get? I get W7 by W0. Right? We are trying to find out what is the WF, fuel consumption. What will be fuel consumption? You started with W0, let's see from here. You started with from here when the weight was W0. Did all the operations and landed here. That time the weight is W7. And assuming that in between you have not done anything but flying, so the difference between W0 and W7 will be the amount of fuel consumed, right? So I say WF is equal to W0 minus W7. This is clear? I start from here W0, this, whatever I want to do, and land it here. So this is the 7th point, right? I started with W0 and final is W7, and the difference is the fuel consumed. Now if I write WF by W0, that will be 1 minus W7 by W0. Now see here. If I multiply all the fuel fractions at different stages, I actually get W7 by W0. I have to simply subtract that value from 1, I will get fuel fraction, WF by W0. So this is such a smart way of getting initial number. To complete this exercise, let us do this. So I will see W7 by W0 will be, let me just write it, 0.97 into 0.985 into 0.852, all those fractions I am writing, into 0.9277 into 0.852 into 0.9917 into 0.995. These are all values of this fraction which you have already evaluated. And if I do this, I get a value 0.635. So W7 by W0 is 0.635. I want to find out WF by W0. Then what will happen? This will be 1 minus 0.635 WF by W0 will be 1 minus W7 by W0, and W7 by W0 you know, so you just put this, but you multiply with 1.06, this is usual practice, that I am increasing 6% because 6% is attributed towards trapped fuel. So in a fuel tank, some percentage of fuel, around 5-6%, you will not be able to take it out. So that is why we are keeping this margin. And if I do this, this will become roughly, if I am not mistaken, this will be 0.387. Okay, please do it yourself before you start asking, sir, galat ho gaya, right? Okay, why we are doing all these things? Again, I go back. You remember, our aim was W0. W0 was, as per the mission, 10,000 plus 800 pounds by 1 minus 0.387, because this is WF by W0, and for WE by W0, we have seen it was W0 to the power minus 0.07. This corresponds to WF by W0, and this corresponds to WE by W0, because our expression W0, we have seen this is W crew plus W payload by 1 minus WF by W0 minus WE by W0. So WF by W0 is here, and WE by W0 I have already explained you in the initial stage. And if you have forgotten, let me see how best I can help. If you relook into my lecture on empty void estimation, there we have given the expression WE by W0 based on statistical data. Again, it is from Raymer's book. It was this, KVS. Of course, this we have taken 1 KVS value. It may vary depending upon the material, composites or any other material, but we are taking 1 here. And for the type of airplane we are discussing, if you see the table to see how the values of A and C, this typically representing a bomber, and for that case the value of A in the table is 0.93 and C is minus 0.07. If you are designing a civil aircraft, then accordingly you have to see the value which is historically generated, generated using historic data. So if I do this, then I can simply write here W0 equal to 10,000 plus 800 by 1 minus WF by W0 minus WE by W0. So W0 equal to 10,000 plus 800 by 1 minus 0.387 minus 0.93 into W0 minus 0.07. Right? So what is our aim now? Our aim is to get initial estimate of W0. So what the best way you can do? You select some value of W0, put here and see whether they are converging or not, or use any numerical method. That's up to you. The example says you take the simpler method. You go on putting some number here and see on the left hand side that is equal or not, and you will find this will converge when, just to give you some numbers, But today's scenario, you can do so many ways you can find out a solution. But what is being done here is W naught, WE by W naught, and W naught calculated. Right? Because, see, the W naught decides what is the value of WE by W naught, because this is given as a function of W naught. Right? That is why we have this sort of a issue. We start with 50,000 pound, and this value is 0.4361. If you use that expression, so that will give you around 61057. If you make it to 59300, then this value is 0.4309, and this is 59311. And if you have 59310, this value is 0.4309, and this is 59309. So almost converging. So you say, okay, W naught initial I can start with as 59310 pound. Right? And then you see from the mission requirement what is the closest aircraft, what baseline you have taken, and you will find that if things are fine, this number should be closer to the number which is being available through a baseline. It cannot be widely different, then something is wrong. Right? We'll also talk about how to get a feel for this number, WF by W naught. Somebody said 0.4, 0.5. What should be the number? So once this mechanically you know how to do it, we'll now put a designer's perspective on how much WF by W naught you should expect for such an airplane. Right? And that is what is the essence of a designer. Okay, thank you very much.